Hello guys, welcome back to my channel, Memo African Motives, working on Industrial Electronics N2, the paper which was actually written in November 2022, which is an X paper. Actually, we haven't been working on Industrial Electronics, this is our first paper, but next year as we are approaching, we shall be working on Industrial Electronics. For those who have been asked in Mathematics N2, Engineering Science N2, yeah, you can have something because we've been working together. But for those who are new, you can consider being part of the family that is Memo African Motives by just subscribing to the channel so that you won't miss any of the classes that we shall be having from Memo African Motives. So without wasting much time, let us quickly rush through the questions, the question paper that we are having. So as we know, guys, your instructions, make sure that you read your instructions, everything that you're given. Because this is for you guys, everything is for you. Make sure that you read your instructions and, so that you understand the questions. All right, on question number one, we are given to refer to the circuit below and calculate the following. So we are given a circuit below, and from that circuit, we are being asked to calculate the following. That's a circuit, that's a DC circuit. Okay, so that is what we had to calculate the total resistance in the circuit, the total current in this and that. That was 20 marks, everything there. All right, so we are not going to waste much time. 1.1 was to calculate the total resistance. So the first thing whenever you're dealing with electrical circuits on DC is to note the flow of current. As we can see, this is our supply voltage. So, and the positive, and we've got our negative here. So the current is going to flow from this side, whereby we have got our total current into I1, I2, and this I2 at this point, it is going to branch this way and also this way. That means these resistors, they are actually in parallel. We are talking about R4, R5, and R6. These three resistors, they are in parallel, okay? On current one, this part R1 and R2, they are in series because this current which flows here is the same current that is going to flow here. Is the same current that is going to flow at this point. So that means R1 and R2, they are in series. Okay, so what I'm going to do is to combine the series part, then the parallel part so that we can have our final answers there. Okay, so that's 1.1. Let's start with the series resistors. That is R1 and R2. So you're going to add them. R1 plus R2. Remember, in series you add. So that is the 10 ohm plus the 20 ohms. So for 10 plus 20, which is going to give us 30 ohms. Okay, so that was the series component. For the meantime, I'm going to neglect this R3 because we are going to use it later on. So just leave it like that. Let's cross-check the parallel part, that is the R4, R5, and R6. What is happening? We know that in parallel, for us to find the total resistance for the parallel circuit, if they are more than 2, that means for us to use product over sum is going to take time. So we are going to use this formula. 1 over Rp is equal to 1 over those resistors, which is R4 plus 1 over R5 plus 1 over R6. That is the combination that we are getting. All right, so the formula, you now can insert the values. We've got our formula here. So now let us insert the values. That is 1 over Rp. So make sure, guys, when you are inserting the values, you are going to insert them properly. Okay, so 1 over Rp, which is the parallel part, is going to be 1 over 4. So we've got 1 over 4. The R5, which is 5 ohms. So it's 1 over 5 plus R6, which is 20 ohms. So it's 1 over 20. Okay, so that's 1 over Rp is equal to there. It's just a matter of calculator, guys. Use your calculator properly. We've got 1 over 4 plus 1 over 5 plus the last one, which is 1 over 20, like that. Okay, so answer is going to be 1 over 2. So as we can see here, to find Rp, we just have to divide by 1. This here, for you to find Rp, there are so many ways. Yes, you can cross multiply this and that, but from our mathematical concept, the moment you divide by 1, you divide by 1, that means you're going to have Rp here. So Rp is going to be 1 over, that is the inverse of this, which is 2 over 1, and that is 2. So you're going to obtain 2 ohms, or from your calculator, if you just divide 1 divide by that answer that you got, that would that is 2 ohms. So that is it, guys. We've got the parallel combination now, which is this part. We have combined these 3 resistors together. Okay, so what I'm going to do, I want us to have this circuit diagram redrawn so that we understand so far where we are. Remember what happened? We combined this series circuit. Okay, let me just have a shorter diagram here. The supply voltage does not change the way it was. That was 90 volts. Okay, so we've got the supply voltage here of 90 volts. Okay, so that is our VT. And remember, we said current is flowing this way, which is our total current. Okay, what happened is that we combined R1 and R2. So it's now 30 ohms. So it's a single resistor now because we've combined this one. So I'm going to represent it with a single resistor so that we know what is happening now. So combining this is now a single resistor, okay, which is of 30 ohms. So that is where we are now having our 30 ohms here. Okay, if we were to cross-check back, we never worked or used R3. R3, we never talked about it, so it is going to remain as it is with 18 ohms. Okay, so we are going to have our R3 here, but there is something that is going to happen now. We combined the series. Okay, let's write so that we don't confuse each other here. Our R3 is still 18 ohms here. That is our R3 still there. But we combined these resistors in parallel and we got 2 ohms. Remember, from this part here, we got 2 ohms. And that means this combination now is supposed to be here. That is where we are going to have it as the total resistance for the parallel. So that means we are going to have our parallel part here. That is where we are going to have this parallel part. All right, so that was our RP, then the RS, then the parallel part, which is of 2 ohms. So here we are going to have 2 ohms. Okay, so the circuit diagram is now reduced to this. As you can see, it's now easier to calculate the total resistance. You're going to ask yourself now, what is happening at this moment? Okay, at this moment, we can clearly see that these 2 resistors, they are in series. The 18 ohm resistor and the 2 ohm resistor, they are in series. So that means we are going to combine them again. Okay, so R series, it is going to be 18 plus 2. Remember what we did, we add in series, so we're going to add, which is 20 ohms. All right, and I'm going to reduce my diagram again so that you understand me, guys. I want you to understand what is happening here. So this 30 ohm is not going to be affected. It's going to remain as it is. But now we have combined these 2 resistors to a single resistor like this. And that single resistor is of 20 ohms. So we've got 20 ohms here, and we've got our 30 ohms there, the supply voltage and so on. Yes, you cannot redraw these diagrams if you understand the concept, but it is important that you just redraw so that you understand what is happening. Okay. Having these 2 resistors in parallel, that means we can have the total resistance because we are just left with the 2 resistors now. So that means our RT is equivalent to the R parallel that we are going to get. But these are 2 resistors, so that means we can use product over sum. So using product over sum, remember, if you have got 2 resistors, guys, so RT is going to be the product of the 2, that is 30 times 20 over 30 plus 20. Then we have got the total resistance of the circuit. All right, let's get back to the calculator here. That's 30 by 20. Whatever that we are going to get, we divide to 30 plus 20. Okay, what do we have there? That is 12 ohms. So we're going to have a total resistance of 12 ohms in this circuit. So that was the question number 1. And with these calculations that we had, we were able to obtain the total of 8 marks. That was 8 marks. That's a lot. Yeah, 8 marks for that. But anyways, we know what is happening there. Okay, let's check the 1.2, the total current flowing through the circuit. Okay, so as you can see, we have our total resistance here. So that means the total current can be taken from there. All right, so I'm just going to work it here. That's 1.2. So our total current from the total voltage over the total resistance. Our total voltage is 90 volts, okay, over the total resistance, which is 12 ohms. So we can divide from our calculator, 90 divided by 12, that is 90 divided by that answer that we got, which is 15/2, that is 7.5 amps. This is current, which is measured in amps. All right, so that was it, guys. As you can see, it deserves 2 marks, just a normal approach that we are having there. All right, then we move on to 1.3, the currents I1 and I2. Okay, this is what is happening here. For you to understand what is happening, guys, it is going to be easier if we are to take this diagram back. Remember when we reduce this diagram, that one, it's going to help us a lot so that we understand what is happening. So I'm going to take this information, I1 and I2, to this circuit that I have reduced here, because working with this diagram is going to be difficult for us. Okay, so this is 1.3. I'm going to take you back to this diagram here. All right, on this diagram here, this is what is happening. Remember, we combined these resistors. We now have our total current here. This is our IT. On the 30 ohm, this is where our first current is flowing, which is I1 in 10 ohm and 30 ohms. So I1 is not going to change. It's still at this point. So this is where we have our I1, and this is where we have our I2. I2, the current that we have on I2 is going to flow in the 18 ohm resistor, in the 40, in the 4 ohm, in the 4, that is the same current that is going to flow, but only that at this point it is going to branch. But that current is the one that is here, that is I2, the one that is going to branch in these resistors. So that is why I'm taking the whole combination of these resistors into a single resistor. All right, so I hope you understand what is happening there. So it's now easier now for us to calculate those currents, because here we can see that the voltage supply according to this circuit is in parallel to this. The 90 volts is found on R1 here. We also have 90 volts. We also have 90 volts. And if there is voltage and resistance, then it's easier for us to calculate current. Okay, so that's 1.3. So that means current 1 is going to be the total voltage over the resistance, that is of 30 ohms. So we've got 90 divided by the resistance of 30. Okay, by just mere looking, this is 3. So it's going to be 3 amps. I2, the same I2 we can subtract since it is the supply. We have got a supply of 7.5 amps, and we say this is 2 amps, 3 amps, sorry. So you can subtract 7.5 minus 3. We've got I2, or we can calculate I2 still using the same concept, voltage over resistance, because we've got the same voltage of 90 volts, but now we've got a current of 20. So if we divide this 90 divided by 20, we can have I2, and we can even prove to see if this makes sense. So this is 4.5 amps from our calculator. Now let's add, if we are to add this to 3 plus 4.5, we must obtain 7.5, which is true. So that means these two currents, they are correct. Okay, so that was question 1.3. Let's see the question on 1.5, which is 1.4. Okay, so that's 1.4 now. We actually asked to calculate the voltage drop across R5. Okay, how are we going to have the voltage drop across R5? Okay, I want you to see something here. Remember what we said, guys. Okay, it's going to be easier. R4, R5, R6, these three resistors, they are in parallel. These three resistors, they are in parallel. That means the voltage drop that we are going to have here is the same. We are going to have the same, because they are in parallel. So we're going to have the same voltage drop. So that means for us to have the voltage drop for this, we are going to use the resistance that we got from these parallel resistors, because we combined them together and we got the RP, which is the resistance in parallel here. Okay, this is what happened here. If you are to cross check, I just want to remove this part. Okay, we calculated RP on this part and we got 2 ohms from this part. So having that 2 ohms and the current, which is I2, because this one is going to be affected by I2 from our diagram here, that is I2. That is the one that is going to affect this current. So using I2, we can calculate the voltage now. So 1.4 we are going to calculate the voltage in the parallel, which is I2 times RP for that parallel combination, which gave us 2 ohms. So I2 is 4,5 times the RP, which is 2 ohms. So if we multiply this, we are going to obtain 9 volts. This 9 volts is the same voltage that is going to be found on R4, on R5, on R6. They are going to have the same. So that means V R5 is equal to 9 volts. That was it. All right. Just like that, guys. The other part, which is on 1.5, was to calculate the power consumed by R6. And that is 3 marks for that to make a total of 20 marks. Okay, R6 is the same resistor that we had in parallel here. And we said, remember, we said the voltage is the same. So which means the voltage here, we've got the voltage from this R6. There is a voltage. Remember what I said here? Okay, let me show you here. I said the voltage across R3, R4, R5, and R6 is the same, which means we've got a voltage of 9 volts. Okay, so that is 1.5. So already there is a voltage across resistor R6, which is 9 volts. And we also have the resistance for that R6. Remember, R6 is 20 ohms. Okay, our R6 was 20 ohms. So can we not calculate power given voltage and resistance? We can calculate power because we know that power can be given by the formula V squared over R whenever we have got voltage and resistance. So power, the power that is going to be found on resistor R6 is going to be VR6 squared over resistor R6, which is 9 squared over the resistor R6, which is 20. Okay, so that's it from your calculator. You can do this. 9 squared divided by 20. That is, we can have 4,05. So this is 4,05 watts. Remember, power is measured in watts. So that was it, guys. On question number 1, it was just a normal consideration that we had. As we can see, guys, this was a normal consideration. All that we have to work with more questions, more revisions, so that we can be able to understand how these questions are being given, or how do they ask these questions actually. Okay, anyways, let's check the other part of the question, which was question 2. Question 2, the first part, we are asked to state 3 factors which influence the capacitance of a capacitor in an AC circuit. What are the factors which influence the capacitance? So the easiest way that you can use to have the factors here is from the formula. I just want you to see this formula here. This is 2.1. Okay, we need the factors that influence. Okay, we know that capacitance can be given by this formula, that is EA over D. Okay, so these are the factors actually that you are given here. So we can talk about the dielectric material. So, okay, so we can talk of the dielectric material, right? We can talk of the area, the cross-sectional area. That is, we can have the cross-sectional area, which is definitely measured in square meters. Then the D, that is the distance between the plates. So we can also talk of the distance between plates, the given plates, or the distance between the given metal, or that is the plates. Okay, so that is the 3 factors that we can have. So as you can see, if you know this formula, you can just take your answers from there. All right, 2.2, we are now given to refer to the vector diagram below. So that's a vector diagram. Remember, sometimes they ask you to draw this vector diagram, but now they've given you the vector diagram. So we are given that there is a supply voltage of 250 and a frequency of 50 hertz AC supply. So that's AC circuit, okay? So whenever you're given this question, you have to study what you're given. You are given XL, you are given XC, and you are also given the resistance. And according to this circuit, we can see that our XL is bigger than XC. So which means our circuit is in favor of the inductive circuit. Okay. Now the question on 2.21 was to calculate the value of the inductor in millihenries. Take note, we are given the instruction in millihenries. Okay, so what are you going to do? Okay, let us just have here the value of the inductor in millihenries. So I'm just gonna write it here. I hope it is clear. 2.21. We know that from XL, because we've got XL there, XL is equivalent to 2 pi FL. So to find L, we can just divide by 2 pi F both sides, by 2 pi F both sides. So that means the inductance is equivalent to XL over 2 pi F. Yeah, sometimes they write this formula like this, sometimes they don't give you like this. So it depends with how you were given. But if you are given like this, then you have to transpose and make L the subject. Okay, so let's fill in our values. Our XL is 39.25. So if we're 39.25 over 2 pi times the frequency of pi, you can use the pi from your calculator. Okay, then the frequency, remember here we are given that the frequency is 50 hertz. So this 50 hertz is frequency. Remember the units for frequency is measured in hertz. All right, so that is going to be times 50. So that's it. We can have our inductance there. So let's, and also take note, we are asked to give this answer in millihenries. Okay, so this is going to be 39.25 over 2 pi, that is 2 pi times 50, like that. Okay, so that is 0.249, something like that. So this part I want you to understand. For you to convert to millihenries, remember millihenries means times 10 to the power of minus 3, that's milli. So you're going to do the opposite. This is to the power of minus 3. So for you to convert to millihenries, you multiply by the opposite, which is times 10 to the power of 3. The opposite of minus, that's a plus 3. So from this answer that you have, simply multiply by 10 to the exponent of 3, or 10 to the power of 3, we are going to have 124.9366, which is 937. So it's going to be 124.937. Okay, so that's 124.937. Automatically, this answer is now in millihenries. By just multiplying by 10 to the power minus 3, you are having your answer now automatically in millihenries. Oh, so that was it. Let's check the 2.22. That is the value of the capacitor, and take note in microfarads. Okay, so the capacitance can be taken from this formula from XC, or if you know the formula, then you can just use your formula direct, because you know that C is equivalent to 1 over 2 pi fxc. So that is our capacitance, which is 1 over 2 pi fxc, just opposite of xc. You can get that. Okay, so that means we can insert our values. That is 1 over 2 pi times the frequency. The frequency does not change. It's still 50 times xc. This is our xc here, 31.8. So it's 31.8. So from there, we can multiply or divide whatever that you have. So you're going to have 1 over 2 pi, that is 2 pi times 50 times 31.8. Okay, so we've got 1 comma whatever that we have times 10 to the power of minus 4. But remember, okay, let's get back here and explain again. Your answer is supposed to be in microfarads, whereby micro means times 10 to the power of minus 6. Just like what we did, milli times 10 to the power minus 3, we multiply by the opposite. So it's the same. For you to convert to microfarads, you just do the opposite. You multiply by 10 to the power of 6. Whatever that you have here, if you multiply by 10 to the power of 6, your answer is going to be automatically in microfarads. So that is 100.097. Okay, so you're going to have 100.097. So it's 100.097, which is now in microfarads. That is how you can easily convert to microfarads. Okay, so that was 2.22. Then 2.23, the impedance Z, that is the impedance, the total resistance for the circuit. That is what we have for. Remember, here we said XL is greater than XC. So which means the impedance is in favor of XL. So our formula for this impedance, as long it is in favor of XL, it is going to be given by this formula. Z is equivalent to the square root of R squared plus XL minus XC. Since XL is greater than XC, XL is greater than XC. If it was XC being greater than XL, then you vice versa here. Okay, don't forget to square here. So Z is equivalent to, let us substitute our values now. We've got our XL, the R, everything is there. This is our resistance, which is 8 ohms. So it is going to be 8 squared. So we are going to have the square root of 8 squared plus XL. Remember our XL here, let's put it somewhere where we can see it. XL was 39.25. So that was 39.25 minus XC, which is 31.8 here. So we're going to subtract 31.8, square everything. Okay, so that is our Z, which is the impedance of the circuit. So I'm just going to use the calculator at once. So that is 8 squared plus in brackets 39.25. Okay, there is a comma there, comma 25 minus 31.8. Then close the bracket, squared. We are going to have 10.9317, but the 7 is going to round off this one into 2. So it's going to be 10.932. So that's 10.932. And this is impedance, which is measured in ohms, just like the way that we use for the units that we use for resistance. So that was it, guys. As you can see, it was a direct question. Let's move on to the other part of the question, which is 2.24. There we are now asked to calculate the supply current. That's 2.24, the supply current. That is the total current for the circuit. Remember, if you have got total impedance and also the voltage, then it's easier for you to calculate the total current, because we know that total current is the total voltage over the total impedance. And the total voltage is the one that you are given here on this information. Remember, you're given 250 volts. That is voltage. So the units there can tell you that is voltage or not. So that one, it's volts, which means you are referring to the voltage. So it's going to be 250. All right, so we are going to have 250 divided to the total impedance, the one that we got here, which is 10.932. Okay, by doing this, if you divide, you can have your total current. So that's 250. 250 divided by the answer of 2.932. So this is 932. Okay, which is 22.868. If you round off, that 6 is going to change 8 into 9. So it's going to be 22.869 amps. This is current, guys, measured in amps. So that was your total current. That was 2.24. All right, 2.25, we are now asked to calculate the voltage drop across the inductor and the capacitor. We know that this circuit diagram that we are given, I mean the vector diagram that we are given in this way, it's actually representing inductor, because if they are now asking you to draw the circuit diagram, this is actually a part where these are in series. And we know that in series, we've got same current. In series, we've got same current. So since we are supposed to calculate the voltage drop across the inductor, we are supposed to use the resistive part, which is, we are talking about XL, the inductive reactance. And on the capacitor, we are supposed to use XC, which is the capacitive reactance. That's what you use for you to calculate the voltage drop. So what am I simply saying here is that on 2.25, we are going to have something like this. 2.25, we have got the voltage across the inductor. So it is going to be the total current times the reactance of the inductor, which is XL. Okay, the total current is there, which is 22.869 times XL. XL is the one that you're given from the vector diagram here. From our vector diagram, remember, guys, XL was there, 39.25. So you're going to multiply by 39.25, whatever that you're going to have here. Okay, so multiply to 39.25, we have got the voltage just like that, guys. Okay, so this is 22.869 times 39.25, and we're gonna have 897.608. Okay, so that's it there. So it's 897.608. Is it 608 or 806? Okay, this is 608. Okay, so this is voltage, which is measured in volts. All right, then we've got VC, which is the same thing, the total current, because it's in series, the current is the same, times XC. So that means the VC, total current is not going to change, going to have the same 22,869 times XC. We now get back to our vector diagram. We can check here below, we've got our XC here, which is 31.8. So we are going to multiply whatever that we have here by 31.8. Okay, so let's multiply by 31.8 and see what you're going to have. That is the voltage across the capacitor. Okay, so this was VL, this is VC. Okay, so let's see our answer here. Okay, I think I just have to shift like this. So this is 22.869 times 31.8. We've got 727.234. Okay, so that's 727.234. Okay, this is 234, guys, which is measured in volts. Okay, so that was your VC. Let's move on to the other part, which is 2.26, the phase angle. So whenever you're given the phase angle, as for me, I actually advise you guys to use the one for cos, which is this formula. That's 2.26. That theta is equal to arc cos resistance over the total impedance. This is the easiest formula that you can use, guys. Arc cos R over Z. Okay, so where is our resistance? So arc cos over the resistance is there from the vector diagram. Our resistance here is 8 ohms. We are given our resistance of 8 ohms. So it is going to be arc cos 8 over the total impedance. Remember, we calculated the total impedance before. Here we got 10,932. So that's 10,932 here. 932. So by doing this, we can have our angle. So let's use our calculator, arc cos. So that's shift cos. Okay, let me shift here. That's 10 over, so not 10. Where am I getting 10? This is 8 over 10,932. Like that, we've got our angle, which is 42,9. 627, but the 7 is going to change up this 2 into 3. So it is going to be 42,963 degrees. Okay, so that's our theta, which is the one that was supposed to be here. That is where you find this theta. This theta is supposed to be here. That is where we've got our 42,963. But it was not for you to represent here. I'm just showing you where it was supposed to be or to be represented. Okay, then the last part was for you to draw the circuit diagram. Like I was saying here, this is a series circuit, which has got a resistor and an inductor and a capacitor. So you just have to draw a circuit diagram like that, having a resistor, inductor, and a capacitor. So we've got a resistor, an inductor, and a capacitor in series. Then definitely the supply voltage, which is the AC. Okay, so you're going to have the AC just like that, guys. So this is just AC voltage. Okay, the AC supply just like this. Okay, so remember it was 250 volts, having 50 hertz. So that's it. You can indicate that's your resistor, your inductor, and your capacitor. You can even write those values that you get, but this is enough for you to obtain all the marks. But you can write the values because you have the resistor, you have the value of the inductor. Remember, we calculated them here. Your inductance here, your capacitance is there. So you can even indicate the value. So that was it, guys, for you to actually obtain 20 marks on question number 2. As you can see, guys, it was pretty clear, yet it needed you to be very, very focused and understand what is the question asking actually. Okay, without wasting much time, let's see question number 3. Question number 3, we are asked the first part to name and explain 3 types of bias that can be applied to a PN junction. We are naming, guys, not only naming, but also you have to explain. So what are the bias that you're going to have on a PN junction? Okay, so that was 3.1. I'm just going to name it from here. So the 3.1, remember, on the first condition, there is no bias at all. So let's say no bias is applied. That is the first condition that can be, okay? So no bias applied. So what does it mean if there is no bias that is being applied? We know that when the PN is formed, no bias is applied when it is formed actually. So this is what is going to happen. The electrons, okay, let me just write here, the electrons in the given region, in the given region of the junction, okay, of the junction here, of the junction will cross the junction. So we are referring to the junction here. So they will cross the junction and combine with the holes. So they are going to combine with the holes to close. Okay, so these ones, they are going to combine with the holes. Where are we having these holes actually? That is the question. Okay, so these, they are going to combine with the holes which are close to the junction. So that's what you're going to have. So actually, when there is no bias that is there, that is what you're going to have. And they can be a forward bias, okay? So we can have a forward bias. So there is no bias, then this time there is a forward bias. So as we know that a forward bias is when it's all about how we are going to connect the terminals, this and that. Okay, so I'm just gonna write. So this one occurs when the external, I'm just hope I'm not going to miss some of the words here. Okay, the external voltage source is connected in such a way that it's positive terminal. So I'm just gonna present, this is positive terminal, positive. I can just write in words, guys, positive. It's positive terminal. Okay, so that's a positive terminal here. Is connected to the p-type. Okay, it must be connected to the p-type. Is connected to the p-type. Okay, so it must be on the p-type and definitely the negative on the n-type. Okay, so that is what you are supposed to have. So it's supposed to be connected on the p-type material, and it's negative on the n-type. Okay, and it's negative, let me just write in words, and its negative is connected to the n-type material. So that one is actually a forward bias. Okay, if you can have this, you can actually have 4 marks. Okay, so what happens from there? Current is going to flow. So there is actually a flow of current. Current flows, okay, where? From positive to negative. So it's going to flow from positive to negative. Okay, so positive, negative. So that was actually just an explanation, guys. You've got your 4 marks there. Okay, then let's see, it can be a reverse bias. Okay, so it can be no bias, it can be a forward bias, then it can be a reverse bias. So what happens when it is a reverse? So reverse bias is just the opposite of what we had here. This time the positive is going to be connected to the n-type material. So the positive is going to be connected to the n-type material, okay? And the negative is going to be connected to the p-type material. Okay, so that is what we have when we are talking about reverse bias. And also in this one, there is no flow of current, no flow of current. Okay, that's a reverse bias. So that is what we have. So this one is just a vice versa of what we had here above. I hope you understand what I'm trying to explain. It's just a reverse. All right, so that was 3.1. Then 3.2, it was for you to define the term peak to peak. Where do we have this peak to peak? How do we define peak to peak? Okay, so that was 3.2. Let us define peak to peak here. So actually, that's actually the value that is measured, okay, between the maximum and minimum values. Okay, so that's the value measured between, okay, the positive, okay, between the positive and the negative, and the negative peak values of a sine wave. Okay, peak values of a sine wave. So that is where this definition is coming from. Remember, your sine wave is like this. We are going to have something like this. So here we are having a certain maximum value and a certain maximum value. Let's just say this is 1 and this is -1. So the peak to peak is measured between the maximum and minimum. That is what the definition is all about. Okay, so that is what we had. On 3.2, it was just for you to define. Then 3.3, they are now asking you to draw a full wave rectifier using two. So guys, understand the question. I'm just going to remove this part. Okay, here understand what you're given, okay? You are supposed to draw a full wave rectifier circuit using two diodes with a center tap connection with a smoothing capacitor and a load resistor. Also draw the output waveform without and with the smoothing capacitor. That is 9 marks for that. Okay, so that is what we have, guys. A full wave. It's actually having a center tap and this and that. So how are we going to have it? Okay, that's it. 3.3. I'm just going to have it here. So this is 3.3. Remember, for a full wave, you are going to have our AC input to the transformer. So our AC input is going to be passed to the transformer like that. Okay, so this is the input that we have, which is actually a sine. Remember, we are going to convert from AC to DC. So this is AC, which is our VP, like the primary windings, okay, then the secondary windings and so forth. So here, that is where now we are going to have our secondary part, where that is where is important here, because we are going to have a center tap. So just have something like this, then we are having our center tap. I hope you guys can draw much nicer diagrams than the ones that I'm having here. Okay, not forgetting, because we are supposed to have our diodes there. So the first diode and the second diode. So here I'm going to put the first diode, the second diode here. All right. Then connect these. Just gonna have something like this. Okay, so the center tap now is supposed to be taken from the center here. That is why it is called a center tap. So it's taken from the center of our transformer on the secondary side. And that's where we are going to have now this capacitor. Remember, they need us to have a capacitor and the resistor, which is the smoothing circuit. So this is now a smoothing circuit that you're going to have. All right, so that's what we just needed here, something like that. All right, so like I said, this is our D1, our D2, then we've got our center tap here. You can just name our points A, B, C. And on the transformer, don't forget to indicate these lines here on the transformer. That's here our capacitor and the load resistor, which is now a DC. So this is now the output voltage. So this is V out, which is now a DC part that you're going to have. But as you can see, it's just easy, guys. This is your secondary voltage, you can just even leave your answer like that. You can just leave. So the question was for you to draw this, not only the diagram, but also the waveform here. We need to have also take note here, also draw the output waveform without and with the smoothing capacitor. So without the smoothing capacitor, this is going to be, it's going to be like, okay, so let's see, without. So without, we are going to have, remember your DC now, when it is out, it will be having a lot of ripples. So it will be trying to maintain, but it won't be that way. It won't be smooth like that. So V out. But if we are now having with the capacitor now, or with the smoothing circuit, then we are going to have, so with smoothing capacitor, with the smoothing capacitor, it is going to be like this. Now we are going to have our output. So it's not an AC. Remember, it's a DC. So we are just going to have, it will be now like a little bit combined together, a little bit combined together. So I'm not going to show like everything here, because it's going to go and go and go and go and go and up to infinity, like that, like that. All right, so this is our V out. So we're gonna have a sort of, okay, this one. So it will be trying like to maintain, to be a straight line, something so it won't be like that. So you have to keep on smoothening it so that it gives you exactly what you want. Okay, so as we know from our values, that's 0 pi, 2 pi, 3 pi, and so on and so on, 4 pi, and so on and so on and so on. Okay, so that's how it's gonna be like. And here we have got when the capacitor at this point, we are referring to a condition when capacitor discharges. Okay, this is where it charges, guys. So the capacitor charges here, capacitor charges. Then the capacitor, remember, it discharges. So here the capacitor discharges. Is discharges. Okay, then we also have the output, which is the ripple. So the output, that is the ripple voltage. Output ripple voltage, something like that. Okay, so having these guys, we can actually collect all the marks. You can have all the marks from that given information. So I'm not going to waste much time. I'm going back to the questions. 3.4, name 3 factors that influence the ripple voltage, that voltage that we're talking about. What are the factors which influence that ripple voltage? Okay, so that 3.4, we want to know the factors which affects or which influence to the ripple voltage. Okay, what are these factors? We can talk of random noise, especially random noise. So we can have random noise in the frequency domain. Or just write random noise. Do not write a lot of things there. Okay, in the frequency domain. Okay, that's domain there. That's an M. Okay, we can also have switching noise. So it's all about noise, as you can see, guys. Switching noise. We can talk of the ripple from the AC, ripple from AC, DC conversion. Okay, we can also have the transient ringing. Okay, some of these are reasons, guys. That's a transient. This is an I, okay? Ringing. It's all about noise again. So you guys, there are so many ways and methods that you can use, and you know, this is theory part. The theory part, I know you can have your own understanding. It's fine. Use that understanding to answer these questions, as long what you are doing is correct. That is what is fine. Okay, indicate whether the following statements are true or false by writing only true. By writing only, just write is true or it's false. Okay, to turn a PN transistor, a PNP transistor on, the base is biased negative with respect to the emitter, and the collector is biased to a higher negative value than the base. This is actually true. That's how we turn a PNP transistor. So this is true. Okay, so that's true. 4.12, a common base amplifier has a 0 degrees phase shift between the input and the output. That's true. That's true. That's true. Okay. 4.2, explain how a transistor is biased in the following region. How is it biased in the cutoff region, in the saturated region? Okay, so let's just see the first one, 4.21. Okay, so we've got 4.21 in the cutoff region. Cutoff region. How is it done in the cutoff region? That is what the question is all about. So is when both the base emitter and base collector junctions are reverse biased. So I'm just going to write here is when both, okay, base emitter. So you've got base emitter here and base collector. And the base collector junctions, base collector junctions are reverse biased. So that's it. That's it there. We are done. Okay, the 4.21. How did I write this one? 4.21. Okay, then 4.22 in the saturated region. Okay, so this is 4.22 in the saturated region. What is going to happen in this saturated region in terms of the connections? How is it done actually? Okay, so here it occurs when both the base emitter and base collector junction are forward biased and the transistor is turned fully on. That is the condition. Okay, so let me write it occurs when both the base emitter, and the base collector junctions are forward biased. Okay, so when they are forward biased, that is where it occurs. And as a result, the transistor is going to be fully turned on. Okay, and the transistor is, okay, what happened? The transistor is, okay, it has to save after some time, so I have to give it some time. And the transistor is turned fully on. Okay, is turned fully on. That is what we have in the saturated region. I think, guys, some of these ones, they are just common things that we are used to. Okay, the 4.3, we are now asked to name 4 advantages of using transistor as a switch. How can we, what are the advantages actually of using transistor as a switch? Actually, there's no way until like what we have in switchgear, so I'm just gonna name a few. There is no way until on switchgear, just like those normal switches that we used to have. So it's better for us to have transistors, okay, caused by what? Arcing. So there's no wear and tear on switchgear caused by arcing. Yes, you can write caused by arcing. So that was the first one. The second one, much faster. So it's much faster actually. So this is much faster switching time. Okay, that's it. Then control over long distances. That one is good. You can have a control over long distances. Okay, so capacitors, they do not mind all those. Also, we can have a small base, okay, a small base emitter current, which is being involved here. A small base emitter current can switch the transistor, the transistor on or off, can switch the transistor on or off. So that's an advantage, guys. We just need very, very small base emitter current just to turn on the transistor. We do not need those currents, this and that. No. It's not required. Okay, so I'm just going to remove this part. Then we follow the next question. We see the next question. The next part we are given on 4.4. It was for you to draw a neat labeled diagram to show the construction. Take note, the construction here. The construction and the characteristic curve of a typical thermocouple. So how does a thermocouple look like on its construction? So that was 4.5. So I'm going to 4.4. So I'm going to start with the construction first. We're just drawing there how a thermocouple is constructed. So that's our thermocouple here. Okay, let me just use another ink here. I think it can be best. Okay, even black is fine. All right, so that's the, remember, we've got the hot junction. These are the metals, metal A and metal B. Then to the cold junction, we are gonna have our cold junction. Let's just say this point. Then at the end, we are going to have the meter connected like this. All right, all right, all right. So that's it here. I hope it's clear then. All right, so just gonna put this somewhere here to indicate the cold region. Just indicate it's a region, this one. It's not a single portion. It's actually a junction, that one. Okay, so we are having a cold junction. The hot junction at this point, that's our hot junction. All right, then we've got two metals here. That's our metal A, our metal B, depending with what you are given them. Then the connecting wires, so these wires are the connecting wires. These are the connecting wires, and that's our meter here. We've got our meter. Okay, I think everything is there. So that's the construction. Also, the question was asking you to have the characteristic curve. Okay, so the characteristic curve is just a linear part, just like a linear. Okay, this is too much. Let me put it this way. We just have the normal way that we have a linear, just like this. Okay, then we have got our temperature. Temperature versus voltage versus temperature, actually. So this is voltage versus temperature, just like that, guys. We're done. Okay, so that was it on question 4.4. They just needed you to draw the construction diagram of the thermocouple and also its characteristic curve, and you can actually obtain full marks. Just like I was saying, guys, you can obtain full marks in this paper. You can collect 100 out of 100 in this paper if you are to see it properly. Okay, anyways, let's see the 4.5. Determine the collector current of a transistor where the emitter current, so let's write something here. So we've got the emitter current, okay, which is 50 milliamps, the base current, which is 100 microamps. Remember the relationship. We want to calculate the collector current, and we know that IE is equivalent to IC plus IB or IB plus IC. I don't know which one do you want to use, but just one and the same thing. So the question is for you to calculate the collector current. So you just have to make it the subject by transposing IB to the left-hand side. So it is going to be IE minus IB, which is equal to IC, which is the collector current. So the collector current is going to be IE, which is 50 milliamps. 50 milliamps, that is 50 times 10 to the power of minus 3, minus IB, which is 100 micro, that means times 10 to the power of minus 6. So by subtracting the two, we can have our current. So let's put in brackets here, 50 times 10 to the power of minus 3. Okay, minus another bracket, we've got 100 times 10 to the power of negative 6. So this is what you're going to have, which is as a decimal, that's 0.04, something like that. Okay, so it's going to be 0.0499 amps. Remember what I told you guys, to convert to milliamps. If you want to convert to milli is times 10 to the power minus 3. So you multiply by the opposite of 10 to the power minus 3, which means you multiply by 10 to the power of 3. So the moment you multiply this by 10 to the power 3, it's automatically in milliamps, which is 49.9. So you can write this as 49.9 milliamps. So that was it, guys, for IC, which is the collector current. That's 20 marks on this question, the whole of question 4. So as you can see, guys, it was actually pretty nice paper. All you just needed was to revise, work on more questions as much as you can. Okay, without wasting much time, we are now given on question 5.1. Assume the basic movement of a measuring instrument is a full scale deflection when a current of 1 milliamps flows through it. The resistance of the coil is 20 ohms. So from that, we are now asked to calculate, determine the multiplier resistor to measure a voltage up to 5 volts. Okay, we have to list something down here. So this is 5.1. So what are we given? Actually, we are given the current. Okay, that is our IM, which is 1 milliamps. Okay, so you're given our IM, which is 1 milliamps here. What else are we given? We are given the resistance of the coil, which is 20 ohms. So this resistance, that's the RS. Remember, it's we are referring to the resistance, the multiplier. So if it is a multiplier, that's a series circuit that we are talking about. So which means we've got RS because we're talking about a multiplier. So we've got RS, which is 20 ohms. And the question is for us to, with the voltage, when it is up to 5 volts. So for the voltage, which is up to 5 volts. So the question is for you to calculate RM, determine the multiplier resistor, which is RM. So how do we calculate RM? We can just take here from the formula. Remember that RS is equivalent to V over IM minus RM. Now you want to calculate RM, so you can just transpose to the left-hand side. It is going to be positive RM. Then we transpose RS to the right-hand side. Is going to be a minus. So this is going to be V over IM minus RS. So it's just a matter of substituting into the formula the V, which is 5 over IM. That's 1 milliamps. Okay, so IM here, it's 1 milli, and we know that milli, that's times 10 to the power of minus 3. Minus RS, which is our RS is 20. So we can have our RM. So that is it. From our calculator, guys, some of these things just needs a calculator. 5 over 1 times 10 to the power of minus 3. Whatever that we have got here, we subtract a 20. And that is going to be 4, 8. So this is 5 volts. Okay, am I sure about this? Okay, let me check. Am I? Yes, that is 5 volts. Yeah, that is it. That is 5 volts there. So that is correct. So we are going to have 5980. Okay, so that's 5980 ohms. So that's what we had from this one. Then the other part of the question now was for you to draw the circuit to show the multiplier, to show how the multiplier should be connected. How is the multiplier connected? Remember a multiplier circuit, how is it connected? That is the question that we are being given. So for this one to avoid, as you can see, it's just 2 marks. So to avoid a lot of things, just draw a simple circuit of a multiplier, just like this here. This is 5.12. Remember, we have got a series resistor, and we have got our multiplier here. That is how our multiplier is connected. So that's it. That's our RS, then our multiplier resistor, and definitely we are going to have the voltage across the multiplier resistor, the voltage across the series resistor, and we know that current is that's the same, the IRS that is going to flow here. That's our IRS and the total voltage of the circuit that we are having. So that is what you're going to actually have. That is our RM. So on this one, it is actually a direct circuit that you are having. Do not write a lot of things from this one. Do not have a lot of things. So it was a matter of you playing around, guys, with the questions. Play around with the questions. I think it is much, much easier that way. Okay, 5.2, we are now asked to calculate the gain of an amplifier which produces a current of 1 amp. I want us to understand this question, how it is given. It produces a current that is the output. So, okay, so that's 5.2. So we are given the output in terms of current, which is 1 amp, and 8 ohm loudspeaker. Whenever referring to a loudspeaker, that's the output. A loudspeaker, remember, it's at the end. So we've got resistance, which is R out of 8 ohms. When the voltage of 300 millivolts is applied to its input, so we've got the input voltage of 300 millivolts, the input impedance to this amplifier, we are given the input resistance. So the input resistance is 100 kilo ohms. Okay, so the question is for us to calculate the gain. Remember that our gain can be given by this formula. NP is equivalent to 10 log P out over P in. So that's it. As you can see, the formula is direct and straightforward because we just need to calculate P out, P in here, which is the input power, and P out from this, because this is the output here. This is our output, and this is our input. Okay, let's start with P in. How can we have the power input? The input power in this case is, we can check, we are given voltage and resistance. So given voltage and resistance, power is equivalent to V squared over R. So V, which is our voltage, 300 milli, remember milli is times 10 to the power minus 3. Then we square that one over the total resistance, which is 100 kilo, means times 10 to the power of positive 3. So that was it. We have got the input power from this. All right, so from your calculator, just have brackets. This is 300 times 10 to the power of minus 3. Whatever that we get here, we square over 100 times 10 to the power of 3. That is what you're going to have. So just imagine the values that we are having. Okay, I'm just going to convert. That's 9 times 10 to the power minus 7. Okay, 9 times 10 to the power minus 7 watts. So this is your input. Okay, after that, you go to the output. On the output, you're given current and resistance. So from current and resistance, how are we going to have P out? So you can just have P out. Let us just have it here. So P out, okay, let's use another mark so that we won't understand each other. So like I said, we've got current and resistance. So power is given by I squared R for that. So it's the output current, which is 1 amp. So it's 1 squared times the resistance of 8. This is direct, which is 8 watts. So the output is 8 watts. And the input, it's 9 times 10 to the power of minus 3, minus 7 watts, guys. Just imagine. So from there, we can substitute into the formula. So NP, which is the gain, is going to be 10 log P out. So that's our P out. Let's insert our values. You can just insert our values here, which is 8 over P in. Remember, P out over P in. P in, it's 9 times 10 to the power minus 7. So that's it. This one, you can even simplify direct on your calculator. That's 10 log, just put a fraction here, 8 over 9 times 10 to the exponent of negative 7. So that's it. We can have, okay, let's put this fraction properly close here. So we can have 69,488. Okay, so that is it. There is 69,488. So it's 69,488 decibels. So that is our gain from that part that we had. So as you can see, guys, it was actually direct because we are given all the values. All you just needed was to take from the given information what you are given as it is. Then from there, substitute the values that you are given to calculate the power input and also to calculate the power output. Then you substitute into the formula for calculating the gain. All right, then let's check the last part of the question where we are now given, okay, let's see. Okay, let's see this part here. All right, so just gonna cross-check this part. All right, sorry for that. I don't know what was happening with this application, but let's just see the last part there. We are given for us to draw a neat labeled system circuit diagram of opposite. Take note here what you're given of opposite direction rotation. So whenever we are having an opposite direction rotation, we are going to have our circuit. I don't know if I'm going to draw this nicely, but I just hope you understand what is happening here. So we're gonna have the first connection. Guys, just pardon my diagram. Just pardon my diagram. Especially when it comes to straight lines, there is gonna be a straight disaster. But I just hope you understand what is happening here. Then we have got our connections that we are going to take from this point to the resistor. All right, to the resistor like this. We're gonna have something of this nature here connected to the one that is from this line. All right, so you're gonna have a connection on this one. All right, so that's where we are having our R1 and our R2 here. Okay, from there, we can have this connection. Guys, my diagram, just mind, do not mind a lot. Just as long as you understand what am I trying to do here. I hope you understand what actually am I trying to do. Okay, so this one is going to the other side. Then here we must have another component, okay, which is another component to the output. And here another component also, if I'm not mistaken there, just hope I didn't leave any component there. All right, then another component connected so that it gives us the same thing that we had there. So I'm just gonna put it a little bit this side. All right, so this one is now a repetition of what we had, something of that nature. All right, something of this nature to the component here, then we can actually join these two. Okay, so my diagram is not that smart, but I just hope you understand the diagram that you're supposed to have. And we shall try by all means next time just to bring the exact diagram as it is without redrawing these diagrams. Okay, those connections that we had are supposed to do the same thing from both sides. So we are going to have here. I hope I'm not too fast. All right, to this side. And this is too much. This is too much. Yeah, something of this nature. Then we've got another component connected together here. So we've got R1, R2 again, just like what we had previously. So you can have R1, R2. So I'm going to name the other components. We've got S1, S2. This is our S3, here, our S2 here, which is the same as the S2 here, our S1 here, S3, and so on. Okay, that is our AC supply. So for the AC supply here. Okay, so that's what we are going to have. So we've got the transmitter and the receiver here. So this is our transmitter. And we have got the receiver on this end. All right, so that is what you're going to have. So the question was for you just to draw, Do not answer the questions that you're not asked on exam. Answer the question, draw a neat labeled, okay, a system circuit diagram of opposite direction rotation. So this is of opposite direction, and for 6 marks for that, to make a total of 100 marks in this question paper, which was written November 2022 for Industrial Electronics N2 from Memo African Motives. Till we meet